notice it goes up to 10,000 megatons of energy released. Thank you. And at the bottom here, you can see a little diagram. This little diagram, you notice, has the same slope as this. This is the energy released by earthquakes. And Cinna's looking at it very interestedly because it's actually from his thesis. Do you remember this? This is page 72. And of course, I should be talking about experimental science because I know Cinna because he loves messing with instruments. And that's how I have, in fact, been working with him. But today I'm going to talk about something completely different, which also Cinna introduced me to, corruption. So just before I get on to this, this is also from his thesis. There is occasionally some confusion between the concepts of plasticity and viscosity, and it may be convenient to define these terms as they will be used here. The law of viscous flow given by Newton, 1685. He's always taking extreme stance. Here he is quoting in his thesis from Newton. And then a little bit further in his thesis, he tells us why buildings don't fall down. It should be noted, firstly, that the presence of low-temperature creep in rocks does not imply a lack of strength any more than it does in steel or other metals. In fact, below a certain stress threshold, the creep is a logarithmic in form and soon reaches a rate, blah, blah, blah. If this were otherwise, no structures of any kind could ever be built, since creep is a universal feature in all construction materials. This is why buildings don't fall down. According to Cinna, 1955. Okay, on to something more serious. This is the death toll from earthquakes in the last 2,000 years. It's getting worse and worse and worse. Here is the world population, which was more or less in control until doctors invented medicine. And then it was no longer possible to go to a city to die. You went to a city to live. And so mega cities exploded, and the world population, as we all know, is completely out of hand. However, here is the invention of seismology. You'll notice this little yellow box. This is our awareness of earthquakes, suddenly quantified with mathematics. And what I want to talk about is why this continues to rise, even though seismologists know all about earthquakes and engineers know all about how to hold buildings up. So here we are. Look, this is the last now 150 years. This is the time during which seismology has been a science on our planet. You'll notice the number of people dying from earthquakes gets up to 2 million in this time interval. We've lost 2 million people since becoming aware of why earthquakes kill people. And at the bottom, I just show you a few events in seismology as a function of time. First of all, Mallet made this fantastic catalogue which almost showed plate tectonics in 1860. The first seismometer was invented about 1885. S-waves were discovered by Oldham, and in 1901 he described the core of the Earth. A massive discovery. Go away. Michelson started asking questions about the rigidity of the Earth in 1915, and Jeffreys wrote about the liquid core. Oldham discovered a core, but he didn't know what it was. In fact, he even speculated it might be gas. So this was a major step forward. And then Richter invented the magnitude scale. As we know, Cinna discovered that rocks were viscous and provided a law for that. Jeffreys modified that a little bit later. Unfortunately, he used the same law to show us that plate tectonics could not work by convection, but we'll forget about that. And there are a whole bunch of discoveries here. But these are important steps in seismology, and not everyone is shown. here are two important steps. Here's Cinna being born between Jefferson's first edition of the Earth and his discovery that the Earth has a liquid core. This is a great moment for our planet. The arrival of Cinna in 1924. Well done, Cinna. And this is the other great moment for me when I met him for the first time. And he changed my thoughts on everything after that point. I was a very naive, stupid student before I met Cinna. After that, I've become outspoken, outrageous, but I'm still stupid. Okay, now that was what was happening in seismology. This is what's happening in earthquake engineering. In fact, people realized they could make buildings quite strong, even in the times of the Romans. But it wasn't until about 1860 that Mallet and Mills realized that buildings just fell down because they were being shaken. The British realized this in 1935, and they actually mandated earthquake-resistant construction in Pakistan at this time. And by the end of the middle of the 20th century, we had earthquake-resistant construction everywhere. But the people kept dying. There's a problem here. And this is the sort of problem that Cinna loves to tackle. What is the problem? Well, here you are. Buildings fall down. 1999, a couple of earthquakes, decent number of people killed, huge numbers of people. Buildings just falling like flies. This is Dusche, in Bhuj, in Sumatra, in Kashmir, in Wenchang, in Bam, in Tohoku, and of course the worst one most recently was in Haiti. And what that means is you can quantify a success. It's not a success, it's a failure. This is that century of earthquakes, and these are the number of people killed every 10 years. It sort of fluctuates, but look, this is the last 10 years. It's the worst ever. This is the worst ever, and yet we've been working at it for ages. Well, you might say, it's simply because the world population has increased. Every earthquake kills more people, obviously. Well, this is the normalized thing. We divide by the number of people on the planet. In fact, it's unchanged in the last 100 years. Nothing has happened, despite all the money going into engineering and into seismology. So where are these people dying? It turns out most earthquakes that kill people are mid-continent. I love this. Cinna is nodding wisely. He said. But this is an important point. The plate boundary earthquakes, which are the biggest, don't kill people because you have lots of warning. You know that you've got to build buildings that don't fall down because every week you feel a little earthquake. It's in the middle of continents where you don't have that you have most of the problems. And in fact, if you quantify it, the astonishing thing is that 84% of all earthquake fatalities occur in 12% of the land area in Asia. And the reason is that in Asia, you have a huge plate, the Eurasian plate, with large plates heading towards it from the south. They're all colliding with this plate, and the region between these two plates is not oceanic, it's not occupied by fish, it's occupied by people. And these blue dots are the cities and super cities where people will eventually die from earthquakes. The red squares are places where people have died. And look, each square that size, 30,000 people dead. This is terrible. This is a catastrophe. And in some countries in this area, there are multiple offenders. People keep getting reminded that earthquakes are killing people, and yet it still happens. So something should be done about it. Iran is the worst. Look, here's the number of people being killed by earthquakes. Here's Iran's population. If you divide one by the other, you finish up with this green curve, which actually reduces. It looks good. But look at this. It's only 0.3%. It's ridiculous. No change in Iran. And in fact, the next earthquake in Tehran may kill 1 million people in one go. 1 million people. Think about that. And here's another measure of failure that is absolutely appalling. We should be ashamed of this. It's fatality forecasting. We can, within 20 minutes of an earthquake, say exactly how many people, well, we can have a guess, a probability, an estimate of the number of people killed by the earthquake, even before the people on the ground know they're dead. This is appalling. How is it done? Look, 20 minutes after the earthquake, all the world's seismometers relay information into Golden, to Colorado, and a location is given, a magnitude, a depth, and an attenuation. You convolve that with a building fragility, a population density, and you can calculate the number of injuries and deaths based on empirical laws that you've developed from the last 100 years of data. You are predicting people dying. If that's not an admission of failure, I don't know what is. This is dreadful. We know people are going to die, and we can calculate how many they will be simply from the seismometers. So the next question, which has already been answered a little bit today, is why do buildings collapse in earthquakes? Well, the answer is usually they've been assembled wrong. Okay, people have got materials and they put them together, but they don't understand why they have to be put together in certain ways. Here's an example of a column failure in Kashmir. Essentially, this column fell off that column because these lumps of steel didn't go through. Look, they stopped right at the column where the joint is the weakest. This is a fantastic example from Haiti. Have a look at this. This is the concrete. You'll notice it's got these little rounded pebbles. They don't have any grip on each other. The cement is made with sand that's been mixed with sand from the beach. It's full of salt. It's got no strength. And what's more, it's made the rebar in it rusty. And the rebar, instead of being compliant and able to be ductile during an earthquake, it's brittle. So they use cheap steel. And what's more, it's shiny. It hasn't got any bumps on, so it doesn't hold on to the concrete. Now here's an example of people putting up a building knowing it needs steel, it needs concrete, together. They don't understand exactly what it needs to make that a strong building. So this is ignorance. And sometimes the ignorance is overt, sometimes it's covert. Here's another example. But it turns out that nearly all the buildings going up now are concrete frame buildings because there's no wood left. In North America, we're lucky there is some, but in most of the world, there's no wood, and if there is some, you use it for cooking or heating. Concrete is weak because it's cheaper to use more sand and less concrete if you're poor. You use brittle steel because it's cheap. You don't use enough of these things. These things are important because they prevent the column from exploding in compression. This is a very simple concept. Once you understand it, you'll never make a mistake. It's like riding a bicycle. But if you think those little bits of steel there are there just to hold the vertical members in position while you pour the concrete, you can get it. You can be rather sparing on it. And this is the result. Okay, here are some very weak stirrups. The building has simply exploded. The column is. This one is. I think it's in Turkey. There's another example. Here, the steel is sufficient. The column is really strong, but it's not being tied to the foundation. It's just pulled out.